like any concept or like problems that they've encountered that they sort of want me to like try to review, go over, explain a little bit more in depth. It's cool if not.
There was this one question, I forget which WebAssign lesson it was. I think it was either 3.2 or 3.3, but it was asking sine x minus cosine x minus 3x equals 3 through the interval -1 to 1. And it was asking if that could be true, like does that fall within the limit? And I was wondering if there's any better ways to figure that out than using Desmos or just like using minimum and maximum values.
So do you mean, like, can you repeat that, what that was again?
It was, I believe, sine x minus cosine x minus 3x equals 3.
Okay.
Over the interval -1 to 1, inclusive.
What do you mean, like, over the interval
of? So like, it just gave me the interval. So like, the values that fall within that interval when you plug them in, from -1 to 1, and it was asking if that is a possible solution, the value 3.
Oh, okay.
So I plugged in -1 and I plugged in 1 and it fell in between those. So it fell in between the minimum and maximum values. But I was just wondering if there's any better ways to know the answer aside from just putting in the interval, the maximum and minimum interval values.
Yeah, I mean, I honestly think that is more of like basically like an edge case thing. So you're saying like, okay, like for I don't know if you can like see me at all. Sort of for this interval, and then seeing if anything in here like solves that, I guess is what you're saying.
Yeah.
This isn't really like, it's like you're trying to solve for X. I mean, I honestly plugging in -1 or 1 is probably like the only way you're really gonna.
Okay.
Because you're not. I mean, this isn't something you can just sort of like solve by doing some inverse like trig functions and whatnot. It's just more of like a I don't know how to explain it. I'm not sure when was that. I haven't really seen anything like that. I honestly feel like normally with regards to these all those like exam problems, they're gonna give you the information that you need to solve it. Generally speaking, if not, like there might be some like little technique that you need to learn how to use in order to do it, which I kind of went over in a past SI session, but I can like cover them again. But for this, I feel like you're not really given much. I don't really still fully understand the question, which I'm sorry. But I feel like for something like this, yeah, like plugging in like -1 and 1 and seeing like, okay, is it all right? That's probably like the best way to.
Yeah, I can probably find it and screenshot it, send it in the group me if that's fine. But
Yeah, if you want to like DM me over group me, you're like more than welcome to do that.
Okay, cool.
Does anyone else have any like questions or concepts that I could like go over? If not, I might just like shoot right into some problems or like some concepts on my own that I think would be like probably good to cover.
Are we gonna cover like everything in general or just one specific section today?
Today, I mean, we have like, I mean, I was planning on doing like 4 over the next like 5 days. A lot of sessions over the next couple of days. So I'm not sure if we're really gonna cover everything just because like an hour is not too much time. But I mean, anything that's like, you know, people are feeling like sort of not comfortable with, or maybe like need some help, like that's sort of, or like even just general problems. Sorry.
Yeah, that's because I was struggling with like kind of like continuity and discontinuity. So I was wondering if we were gonna work on that.
For sure. I mean, I can go over that right now if no one else has anything to go over. Because like honestly, I'm really here for you guys to sort of just like elaborate on concepts and stuff. So
wait, can you go on? Oh my god. Yeah, no, like after you like go over the question thing, I just have like a question on the homework.
Yeah, for sure. If you want to like screenshot the question and then DM me on GroupMe the actual thing, that's like optimal.
So like for like anything regarding continuity, like I have more like homework problems that like I think going through would make it easier to understand the like continuity. So should I just like screenshot the problem sent. I don't like.
If you want to do that, you can. I have an example here, actually.
Oh, okay, we can do that.
That I think doesn't do it too in depth and doesn't do it with specifically like actual functions, but
Yeah, we can do
graphically,
that.
I think does a great job of like sort of laying everything out. And I sort of covered this actually in the session that I posted on YouTube, but I can still do that. Or are you having more trouble with like continuity when they sort of give you like a piecewise function and then like figuring out like questions about continuity or like the limits from that? Or is it just like
Yeah.
looking at the graph?
Well, we can just, if it's easier, we can just go over the problem that you're about to like go over, and I can just see if it works with what I'm struggling with, and if it doesn't.
Yeah, for sure. And I think everyone should be okay with this just because it's like covering like general things. Hopefully that's like fine. I'm sorry if I ever stand in like the way of anything. I just feel bad. Okay. So I'm gonna try and draw this out like really fast. Like one size. Can you guys list off anything else that I might be able to get to today or in the future? Just because I need ideas for covering like 5 hours worth of stuff over the next couple of days. And I'm not very creative.
Like points of discontinuity, like continuity.
Continuity, big thing. Okay.
Also, like how to like, yeah, like what Lily said, but like how to like figure it out from like the equation.
Yeah, for sure. I wish I recorded the session that I did. Okay, that's like fine. Can you all see this pretty well?
Yeah.
Cool. I wish I recorded the session from what I did a few days ago, just because I actually did cover something similar to this. But I can just like do it again, and it's like not a big deal. I'm just gonna. There we go. Okay, so what can you like tell me about this? Like, what are some observations, just generally speaking, that you can sort of make about the graph I've drawn up here?
There's a jump discontinuity.
Okay, yeah. Where?
Removable.
Where's it? Where's it?
So the removable is where x is 0. There's a dot and 1. So, and then like it's supposed to be 2, but it's 1.
Yeah.
Right.
So you're saying that right here at x equals 0, there's a removable discontinuity right here, right?
Right.
Yeah. Okay. Cool. So x equals 0. Okay. So what were you saying about a jump? What was someone saying about a jump discontinuity?
And then the jump is from x1. Yeah, and then
At x1, right?
Yeah.
Yeah. Cool. Okay. So those that sort of covers the different, different types of discontinuities that we have, right? Unless we have we also have that infinite one that Bradshaw covered today. Actually, there's one that he was like, oh yeah, I guess I could just do sorry, I'm cheating a little bit. This ends here, and then this kind of goes, and then down, right? Okay. Right. Okay. So this is like the three types of discontinuities that we have right here, right? So the best way to sort of describe what a discontinuity is that you can just draw a line through the entirety of the graph without picking your pencil up. And you know that no matter where the point of your pencil will be on that graph, the function will be defined at that input value. So what I mean by that is if I did from 3 to 4 right here, try dragging my marker in between these intervals, obviously there's not any zero non-defined points where there's really nothing there and we're not sure what the value is, right? I can just be like, okay, boom, and everything is good, right? So that's sort of like the general definition of continuity. So the best way to sort of figure out when something isn't continuous in the first place is checking to sort of see like 3 cases on whether or not something is discontinuous at all. And obviously, like from the looking at a graph, which I'll go over like probably right now, there are again 3 main ways that you can sort of see it right here, right? So clearly, like if I'm following along from the right side over here, I'm following it down, I can just keep going to infinity. But then there's like has to be this like, there's a difference between here and here. So I can't just like not move my marker to that point without lifting up my marker, right? So that's clearly like infinite discontinuity. Does that make sense?
Yeah.
Awesome. And then right here, if I start at 2 and go here, I'd have to like do that jump, right? Okay, so that makes sense. And then right here, if I go here, even though I'm going to this point 2 at x equals 0. That was really not smart. Even though it should be going to 2, it's not because it's an open circle, right? And then it's actually defined at 1 for whatever reason. One of the only reasons why this would ever be the case is for like a piecewise function or something. You can have these removable discontinuities in regular functions that aren't piecewise. One example is just f of x equals x squared over x. If you plug that into Desmos, you'll see that it's basically the exact same line as f of x equals x or y equals x, except at the point x equals 0, there's like it doesn't exist, right? It's undefined. Okay. So yeah, there are removable discontinuities, right here, and there's sort of another point where it exists, and then jump and infinite. Okay, that's awesome. So now I want to ask just some like limit questions to you guys, so that we can maybe like figure out a little bit about mathematically and like actual math terms, like what all of this sort of means, and maybe try to draw some connections so that we can like sort of see how it'll actually end up being like in the exam, or like, when you're looking at trying to make observations of other graphs, sort of like going the other way, if that makes sense. Okay, is that cool? Is that all good? All right. So first I want to start with, you guys can see like all the way over here, right? Yeah. I'm going to start with A. So let's look at the limit of x goes to 0 of x. Oh, sorry, you didn't see that. This is g of x, by the way. I didn't define this function that's right here. Okay, so I wrote this limit out. Does anyone have any clues as to what that might be and how you got it?
Does that say as it approaches 3?
It approaches 0. So that's the limit of g of x as x approaches 0. Sorry.
No,
That
you-
like really drawn poorly. I have awful handwriting.
Can I guess?
Yeah, like say anything. Yeah, for sure.
Is it 1?
So why do you think it's 1?
Because it's like not defined. Or like, oh, could the limit be 2? It's just not defined at the limit.
Yeah, exactly. So when we're dealing with limits, we're not dealing exactly with the value that we're sort of just like plugging in at like the x equals 0, right? Like we're not dealing with exactly what the output is if we plug in 0 for x into g of x. Does that make sense? So like we're sort of like getting there almost. We're like about to go to where x equals 0, but we're not just there. We're like barely close. Like I'm talking like 0.0000001, 0 multiple zeros to 1, like off. It's very close, and it just barely approaches this number, this output value of 2, right, from both sides as well. Can you see that?
Yes.
Yeah, sorry.
Awesome. Okay, cool. So we sort of like agreed that this limit is 2. Great. I'm also going to get like rid of this like number system. So what about just g of 0? Can you see that?
Oh, so the
One.
limit, yeah. So the limit would
Yeah.
be 2, but g of 0 is just 1.
Yeah, exactly. So you can see that when you plug in 0, again, as you said, it's just like 1. Yeah, perfect, for sure. So this specifically can actually sort of demonstrate what it means to have like a removable discontinuity. So if we say that the limit as x, and you've seen this before, approaches a of g of a, or some function, does not actually equal g of a, then that implies that there's that removable discontinuity there, right? Because we found that right here, 2 obviously doesn't equal 1. And you can sort of see it right here as well. Does that sort of illustrate that a little bit? Where you can kind of see like, oh, okay, like this has one value that it like evaluates to, and this is another value. And because those aren't equal, therefore there must be a discontinuity, specifically a removable discontinuity, right?
Right.
Yeah.
Awesome. Okay. But before I get to the jump, I want to talk about why we were able to make this limit, why we were able to write out this limit as just going to 0 and not going from both the right and left. You see what I mean there? It's like, why were we able to just be like, oh, the limit is x approaches 0 and not the limit as x approaches 0 from the right? Yeah? It's like, why is that? Why can we do this without having to like do anything like that first? And that's a poor question. Like, sorry, I can try out something else.
Because you can see it in the
Because,
graph.
Yeah.
Yeah. You can see it in the graph. That's true. But I'm looking for a bit more of like a mathematical definition.
Is it because like it's continuous?
So,
Oh, it's not continuous.
equals
It's
zero?
discontinuity.
are you talking about at x equals 0?
Isn't it because the left and right side like exist, the limits exist, but they don't equal one another?
That's closer. That's definitely like getting to the idea where I'm trying to go. So the reason why we're able to do that is because while they do both exist right here, while the limit to x equals 0 from the right and from the left both exist, the important thing is that they're equal. You see that? So if I did the limit of x goes to 0 from the right, this is like different. This is that's 2. Okay, sorry. This is 2, right? And then if I do the limit of x approaches 0 from the left, as you can see here, start here. All right, that was the sound effect, whatever. Okay, that goes to 2, right?
Right.
You can see that. Okay, so they're the same.
Yeah.
Awesome. So what that means is that there's literally no possible way for there to be a jump discontinuity at that point, right? So we can say like, oh, okay, lim as x goes to 0. I'm so bad at writing stuff. As x goes to 0 plus g of x equals lim 0 minus. Right? Because it's we literally just did it. And you've seen this again, you've seen something like this before, just generalized, right? So you've seen x approaches a on the right of like g of x equals lim as x approaches a on the left, g of x. Right? And that means that you're allowed to do just a lim x approaches a. So if the limit of like a function to a single point from both the left and the right are the same, then we can say that a limit exists at that point, right? But that doesn't mean that it's the function's actually defined at that point, right? So there's kind of like a little caveat. Does that make sense? Do you see that?
Yeah.
Like the limit can still exist at a point where there's discontinuity.
Can you say that again?
So like the limit can still exist at a point where there's a discontinuity.
Yes, that is a very big concept and point to make, that the limit right here is still exists. It still is 2, still is something, even though it's not defined in the function for x equals 0, right? G of 0. But that only works if it's for removable discontinuity, right? Because this is the removable, okay? If we transition to jump, there's a bit of a difference there. Okay, are we cool to like move to jump, or is like is continuous, like is the removable stuff sort of like clear, a bit cleared up?
Yeah, well, like that one makes sense.
What do you mean, like right here?
No, it makes sense. Yeah,
Awesome.
like thumbs up.
Okay, cool. So let's look at x goes to 1. Yeah. So I'm gonna off. Okay, do you like see this at all? No, it's too light. Okay, let's do the This is great. All the markers over. Sorry, guys. That's better. Okay. Can you see that? Literally no. Oh my god, I'm sorry. That's literally awful. Okay. Let me write it out one more time, and then hopefully you'll be able to like. Okay. Is that better? That's a lot better. Okay. So what is that?
Is it
What did that evaluate to?
still 2?
Can you say that again?
Is it 2? Is x approaches 1?
It goes to 1. So as x goes to 1, you're saying that the limit goes to 2.
Yeah.
Okay.
Doesn't it like wait? Because like it's going to like different places. Because like on the left it's going to 0, but then the right is going to 2. So would it like not exist at 1?
Mm-hmm. That is an interesting point to make, because if it goes from the right, it goes to 2, right? But if you go from the left, then we go to 0, right?
Mm-hmm.
See that? So therefore, this limit specifically,
Does not exist.
yeah.
Okay, sorry. So the reason like it doesn't exist there, but it exists at like x, like as it goes to 0, is because it's like just the removable discontinuity. So like they're both going to the same places from left to left and right side. But the reason it doesn't exist at x equals 1 is because from the left and the right they're going different places.
Yes.
Okay.
Exactly. So if we write out, so I guess we can be like, can you even see this? Why? Well, let's write out the limit as x approaches 1 from the right, as you guys said. Okay. So we're trying to go to 1 from the right. So if we start all the way over here, we go down. Okay, that won't work. Okay, whatever. We'll start here. And we go, and hit this, right? So we're at x equals 1, and we're from the right. So therefore, the limit is just 2, right? Does that make sense?
Yeah.
Okay. Oh, shit, I did not write feedback. Okay, awesome. So what about the limit of g of x as x goes to no, oh my god, okay, sorry. Goes to one to the left. You can tell me what that is. You kind of already answered it. Someone did.
0.
It's 0, right? Because it comes from the left. And it goes like down, boom. Awesome. 0. Okay. So what does this tell you mathematically in like math terms? Not graph terms. What does this tell you?
The limits are different.
Yeah, the limits are different, right? So we can say that, hopefully you can see this. Not equal. Right? So you can see here that the limit of g of x as it goes from the right is different from when it comes from the left. So, I mean, we can plug these values in. Clearly, 1 is not equal to 0. So what does that tell us in math terms? If we hadn't looked at like the graph, if we only were dealing with this, what would that tell us then?
There's a jump discontinuity.
Yes, there's a jump discontinuity.
When do you decide to either write does not exist or like positive infinity or negative infinity?
Like for what the limit is.
Right, because I remember reading on the textbook that when the limit does not exist, you can write it as an infinity. Like
In a
instead of writing
way.
does not exist.
So I'll explain that in a second. I understand like what you're sort of like getting at.
Okay.
So the other thing I'm trying to get out of this is that not only is it like the limit doesn't exist is what someone's or there's a jump discontinuity, right? But also that the limit doesn't exist when it's coming from both sides, right? And that's exactly what we showed up here. Right here, right? So the first thing sort of that you do when you're shown like a function or like a limit, how do I say this? Like a piecewise function, even better, a piecewise function. And I can get to an example of showing this in, like later on if people want me to. You want to make sure that first the limits at, for example, x equals 1 are the same from the right and left before you can say, oh, it might be continuous. Because then once you have said that they're equal right here, right? Like what we did right here, we still need to show that this limit, because this basically implies this up here. Did you see that? So like, since these limits are the same, that allows us to write this that the limit from both sides goes to the same place as these do. Then to further prove continuity, to like finalize, okay, this is continuous right here in this interval, then you need to plug that value actually in to the function, not take the limit of it, but actually plug it in. Does that make sense?
Yeah.
Yeah. Cool. Cool. So, with regards to the infinity thing, if I were to write limit of g of x as x approaches 2 from the right, and I'm not sure if we've gotten to this in lecture yet, but what would that be?
Wait, is x approaches 7?
What'd you say?
Wait, does that say as x approaches 7?
2, sorry.
2? Okay, no, you're good. You're good. Okay. Would that just be negative infinity?
Yeah, so it's negative infinity, right? Because we're like going like way down. Like literally like it does not stop. It is going straight down to the middle of the earth, right?
So how do you?
Wait, does the
You can go
does
ahead.
the limit not exist? Okay, does the limit not exist? I thought the limit wouldn't exist at x equals 2 because from the left and the right, it's not the same.
So let me get to that. Let me continue. So lim of x goes to 2 from the left of g of x. What is that?
That's 0.
0, right? Okay, cool. But these aren't the same, are they? Negative infinity is different from 0.
Right.
Say this goes to 2 g of x. Notice, sorry, that's a shitty 2. Notice it's not from both sides. It's just the limit of both sides. Then what would it be?
Does not exist.
Yeah. Danny and Matt. So very rarely, if not, I don't think it's. Actually, there's like one case. Very rarely will you ever get a one-sided limit that doesn't exist. All right, that's like a very fringe, strange case. However, it can be quite often where the limit from both sides does not exist. Yeah. So one place where you could see this all the time is in like a piecewise function like this. So there is some function out there that sort of resembles what I've drawn up here as piecewise. And right here, clearly like, okay, this could be like some quadratic flipped on its side thing right here, right? But then it would be like, oh, but it only goes to 1. And then this is like some linear equation, something like that. So you can see that like that's piecewise. But if you look up the graph for just like 1 over x or something, which I don't know where to draw this. I have room over here. Oh yeah. Correct me if I'm wrong, but I'm pretty sure the graph of 1 over x looks something like that. Sorry if you the light, it makes it hard to see. So it kind of goes like this. Yeah. So if you try to take the limit of that, so say this is f of x. Try to take the limit of f of x as x approaches a 0, right? 0. That won't work, right? That's a DNE. But if you take the one-side limit, say from the right, lim of f of x approaches 0 from the right, where would that go to, right? Like where would that be from? It'd be from that side, right? So it kind of go like, and then go to infinity, right? Does that make sense? Yeah, I see some nods. Sorry,
Yeah.
all your faces are very small on my mini laptop. Okay, so that would be infinity, and then from the left, try to just quickly write it out. It's oh wow, that's like an 8. There. That's to you didn't see that. Like, no, sorry. Okay. That's it. All right, sorry. So you can see how like this is an infinity, that's a negative infinity, but they don't exist. And then when they're coming from the same place, right? Does that sort of like elaborate a little bit on what you meant by like the whole limit to infinity, like does not exist thing?
Yeah.
Really? Okay. Fantastic. Glad to cover that up. Does anyone know of an example function where the one-sided limit may not actually exist. Okay, no one's talking, so I'm assuming you're sort of like not really sure of an example. One example I think is if you do something like sine of 1 over x, or something similar to that. If I could just draw it out real quickly. If you do like sine of 1 over x, it kind of does something where it goes like, okay, here's your normal sine thing, but then it kind of keeps going like this and it goes like, and then same thing from over here, like, and then it gets like kind of smushed together, right? And so because it kind of gets smushed together, and they get like they're like the oscillations are really fat and like kind of big, and they stay the same, but they're like getting smaller between each other. You can't really tell where it is, where it's from, right? And there's like some function where somehow I don't think it's piecewise, where this only happens on the right side, right? But it's like normal on the left, or something like that. So from from like this right side, like there's no limit. Does that make sense? Can't really like tell where it is. Hopefully.
Yeah.
Do you think we'd be given a problem like with that specifically?
I doubt it, honestly. I think that's just like a fancy thing to like that like exists, but I don't really think you guys need to worry about that much. To be honest. I don't think that's really something important. I just wanted like just to like demonstrate like, okay, yeah, like one-sided limits can be like does not exist, but it's like very fringe case, does not happen too often. Whereas these limits from both sides, that happens all the time, especially piecewise functions. So yeah. Okay. Cool. Does anyone have any more questions relating to continuity and graphing or just like limits? Because I could go into another one where we start with a piecewise function, and then like I could elaborate on that a little bit and figure out how we could tell, where are the discontinuities, what kind of discontinuities there are, where is it continuous, things like that.
There was a problem in the homework which they give you a rational function and it tells you to determine the point of discontinuity. And then it tells you like either to state the type of discontinuity. I was wondering if we could go over that.
Yeah, for sure. So by rational functions, do you know what that like sort of means?
What it means to be like what a
Yeah,
rational.
like what a rational function is.
Just fraction.
Yeah, isn't it just a fraction?
Yeah, it's like a fraction of like a polynomial or something, right?
Yeah.
Exactly. So I'm looking at this one example. Typically, when you're dealing with rational functions, you're gonna have something on the bottom, obviously, right? And they're very rarely not going to give you something on the bottom that's not either factorable in some way or already in the form of like x plus 1, x minus 1, where you can sort of like tell where the zeros are, right? And by zeros, I mean like, okay, where, for what like values of x is this denominator 0, for example. So I can like write something out real quick. Is it cool if I erase some of this?
Yeah.
Awesome. I don't know where to start. I guess I'll just start from over here. Okay. So yeah. Okay. So yeah, when you're sort of dealing with those rational functions, typically when it's not going to be when the bottom's at 0, that point in like the domain, it's going to go to like infinity where that limit is. And I'm sorry, that's like really poorly explained. My mind is on erasing the whiteboard and not on math at the moment. Sorry, I can't multitask. Oh. All right. Let me see if I can draw this out a little bit. So we got f of x equals x to the fourth minus 2x minus 7. Something to note is that I doubt there's no chance that anyone expects you to just be able to like graph this perfectly. Just like 100% like boom, I know how to graph this. Amazing. I can just picture it in my head. Like that's literally absurd, right? But where do you guys think we should like have we talked at all about like asymptotes or anything in lecture? Because I don't really remember anything like about that. And that's sort of like what I'm getting at, but I can go into that.
I don't think we did.
Right.
but
You know
I'm
what like
not sure.
asymptotes are?
It's like where the graph, it's like a point or like a line where the graph like approaches, but it can't touch it.
Yeah, it's basically where like instead of going to a point of removable discontinuity, it instead just goes to infinity or negative infinity and like never touches that one point. Like gets very, very close, right? So typically when you're dealing with rational functions, you're always going to have those vertical asymptotes. So I'm just going to like draw this out really quickly, and then I think from that drawing, be able to explain it a little bit. So here's our coordinate system. We have -1, 1. And then, that was really nice. Kind of like this. All right. So from here, let's see. Sorry, this is really a terrible drawing, but there we go. So say you're given this rational function and they're like, okay, where is it discontinuous? Is that kind of the question that you're sort of like talking about on the homework?
It said like find the point of discontinuity, so I guess yes.
Yeah. Okay, cool. So the points where any function will be discontinuous are either where it's in a piecewise function and it's explicitly like left out of being assigned anything in the domain, or when you are like mathematically not allowed to plug anything in to like a function into like some function, like it's just like it breaks some kind of law. So when I'm talking about like laws like that, I'm sure you guys can like recognize these. I'm talking like when there's like some constant a over 0 in a denominator, right? Or if you have like in a square root, like a negative b, you can't have a square root of like a negative number, things like that, right? Does that make sense?
Yeah.
Yeah, okay, cool. So if I was given this function, which I'd be looking for when the denominator is 0, right? Like that's sort of signifies like, oh, it's a discontinuity because there's literally never going to be a time when I'm allowed to plug in 0 into the bottom and then like get an output from it, right? Because what discontinuities really are, especially for these normal rational functions, are basically just points that we're literally not allowed to plug some number, some specific number into there, right?
Yeah.
Yeah. Okay. So I put this as -1 and 1, right? As like the points where sort of like where the graph, the function of avoids it. Why do you think I did 1 and -1?
So they can cancel out.
What did you say?
Oh wait, do you mean the graph?
Yeah. So like, why did I know that -1 and 1 are values of x that I can plug in here that will never work?
Because they like make if you factor out the denominator, they would make it equal 0.
Yeah, exactly. So I can sort of rewrite this function. Sorry if you can't see it right now. I'll move in a second. Right? So did that factor make sense on the denominator?
Yeah.
Because that's like the product of like whatever they're called, like the plus minus squares or whatever. I forget the rule. What should I say? Yeah. So what that means is that if x is -1, so for over here, the -1 plus 1 is 0, right? And the 0 times literally anything that this is going to be 0. So 0 can't be on the bottom. And if it's 1, 1 minus 1, 0. Again, 0 can't be on the bottom. So it wouldn't work. So that's sort of how we found out these points where the graph sort of just like dodges. It just really does not want to go to 1, to hit 1, does not want to hit -1, right? So that's like the main way, if you're given a rational function, to find where the discontinuity is to basically be like, okay, am I dealing with a square root type thing? Which, I mean, you could be. I feel I could probably find the example if you wanted me to. Or you're dealing with like a fraction thing like this, where it's like, oh shoot, you gotta watch out for the denominator being 0. Yeah. Yeah. And like other things could be on the bottom as well, right? So like what's the word? So like sine of x could be on the bottom, for example. And so you'd have to avoid all the times when sine of x is sine of something is 0. So anytime you plug in like sine of 0, sine of pi, sine of 2 pi, things like that, then it would be like, oh, then there would just like always be avoiding points along sort of that graph, right? Is that sort of what you were like sort of wondering about?
So if the number, so the discontinuity there, would it be just like negative, like the point, would it be just -1 or 1?
Yeah. So it's not really like a point. It's more like it's more like a value of the domain that is sort of
Okay.
left out. It's sort of like a value of x that is left out of the domain that you can't like define an output value for.
Yeah, so would it be -1 and 1 or just, oh, okay, it would be both.
Yeah, it'd be both, unless they were explicitly like on the domain from 0 to infinity. Then you have to like sort of ignore the -1, right? Because then they're like they don't give a fuck about like anything. They don't care about anything over there. They're just like only this side. Or
Okay,
only this side. Yeah.
gotcha.
Yeah.
So would you be able to tell from just the equation if it's like either left or right, if it's like right continuous or left continuous, or would you just have to plug it, like graph it?
So the only time you'll ever need to worry about that explicitly is if you're given a piecewise function. Because if I'm just given like, again, I think I used this example before, x squared over x, like there's no way for me to only plug in the right side of values into this, right? To like figure it out what it is. Like that's just, it's something that's not possible.
Yeah,
So if
okay.
you're just given like a function, the only times you can really plug in anything for that.
Yeah.
Like if you do the limit of it, the normal function, it's either going to go to like negative infinity, which you won't encounter, and you should not be encountering any limits where like something would go to negative infinity because, I mean, you just shouldn't be at this point. But you will, but for like piecewise functions or something, that's the really only case where you'll have to be like, oh, I need to make sure that like these two functions sort of line up together, and like point at the same value of like output value to then like figure out for the future. Yeah, because like yeah, I understand what you mean though. Like you can't like plug in.
I
you
get
can't,
it. Yeah, that makes sense.
Sorry, I'd elaborate more. Sorry, I'm just
Yeah,
like
that's
talking.
okay. I got it. Thank you.
Yeah. Cool. Does that clear up some stuff? I can go over like another quick like piecewise function problem. I think Jess was here the last time I did it, maybe. So I feel bad if I like redo it, and maybe Lily might have been too, but that was a good example. But I don't have to. If there's any other questions about other concepts.
I'm a bit confused on. I seen like on the homework yesterday, there's something about like. I'm confused on how like tangent and like secant and like stuff like that like comes into this.
So like trig functions and like continuity and things like that.
Yeah.
Okay, so each of the trig functions. Can I erase all this, by the way? That's okay.
Yeah.
So all the trig functions have a pretty distinct look to them. I mean, it's just generally in a math class, it's good to know like what they generally look like and sort of what their general domains sort of are, right? So I can draw out some of them real quickly right here, like sine of x right here. Hopefully you guys all know what this looks like. It's like this, right? It's just kind of this like wave look like pattern. And that has an infinite domain, right? So you can plug any value of x in and get something out of it. Sorry, I just want to check my notes to see if I have anything follow. I'm just so cosine of x. Very similar, sorry if you can't really tell, but it starts like at 1 rather than at 0 when x is 0, right? And I have a handy dandy little unit circle method that I can go over another time if you guys like need help like sort of like evaluating trig stuff like on like quickly. I can do that another time because it'll take me like a second to sort of explain it. But that's like sort of what those look like. So that's like domain, right, for those. If I'm just gonna like look up tangent real quick. I know like generally what it's like, but I don't want to like mess up the specifics. Okay. So tangent sort of looks funny. It's like this. It's like pi over 2, and then negative pi over 2. It goes kind of goes like this. Oh shit! It goes to the middle. Okay, sorry. It goes like this. Yeah. That. Hopefully that makes sense. So there's kind of those discontinuities right there. You see that? And how there's a difference between like, okay, this has like a fully continuous range, where this is like there are some jumps between vertical asymptotes there. Yeah. That's sort of what you were talking about.
Yeah, I think so.
Okay. If you have like another problem, I could, because are you talking about like with limits and like trig functions in general, or like continuity? Because there are also some like specifically like limit problems that I could work on doing like another time, or I could like try to throw up an example really quickly. as well. So like if you were, for example, dealing with like sine of x, sine of x. Are you saying like something like this?
I don't think like that. Actually, I don't really remember. Like, I don't think it looked like that. I'm not sure, honestly. Like, I low-key forget.
Okay. Just like you sort of just reply this like in any other sense that you would with any other limit, where you just kind of like plug in pi over 2 for there, and pi over 2 is the 90 degrees one, right? So that's just like one. Yeah. Hopefully that
The
makes sense.
range of sine x and cosine x are -1 to 1, right?
Yes. That's true. They're only -1 to 1 because they're like ratios, sort of. That's the best way that they're described as. They're ratios. Same with tangent. They can't really go to like over 1. So they're sort of bounded by this invisible sort of like lines. And these aren't really called anything, but that's just like how the sine and cosine functions sort of look. Whereas tangent has like a really wide, I mean, it doesn't really like it, this pattern sort of repeats to infinity in both directions, but at like pi over 2, and negative pi over 2, they're undefined because tangent itself is like sine x over cosine x, right? So I don't know if I need to explain this, but and at pi over 2 specifically, which is sort of like here on the unit circle, see that? That's 1 for sine. So tan of pi over 2 equals sine of goes 1 on the top, and then cosine of pi over 2 is 0. Yeah. So therefore it's like 1 over 0, and that doesn't work. So that's just an example of like why it's sort of like discontinuous at those intervals, right? Does that make sense?
Yeah.
Hopefully. Okay. Cool. Sounds good. Do you guys have any other questions or anything? We're like pretty much out of time. I think I covered a little bit. It's cool if not, or if you have any like ideas for like something that I can like sort of prepare for next time. I do have like specific problems that I can sort of like spend time on in the future rather than like doing concepts. And I will send that midterm exam, the practice one, out, excuse me, as well, like tonight. So
I would just say if you have any problems that like you think we're likely to see, or like big topics that you definitely think we need to be ready for in future sessions, if we can go over those.
yeah, for sure. There were a couple sessions where there's one session where I sort of went over a bunch of different like methods for solving some specific limits that are like the more tricky versions of limits that I think like everyone sort of needs to like be able to recognize and understand. So I can definitely go over some examples of those. It might be like repetitive from the last time, but I think that's fine if like a bunch of people are here, and I think everyone can sort of like use the practice as well. So I can definitely do that.
Okay, thank you.
Yeah, thanks so much for coming, guys.
Thank you.
Appreciate it. And I'll like upload this on like the YouTube and stuff. That's no big deal. All right. Okay.